We've all heard the idea that black holes are cosmic monsters, rogue vacuum cleaners swallowing stars, planets, and maybe even time itself. But what if that's not quite right? The reality of what a black hole does to time is far more bizarre and profound than you might think. The idea that time can just be devoured, erased from the universe, is a pretty chilling thought. But the truth, which is woven from the very fabric of space-time, isn't about swallowing. It's about twisting, stretching, and warping reality to its absolute breaking point. In the next few minutes, we're going to take a trip to the edge of a black hole to find out what really happens to time. And I think you'll find that the universe isn't just stranger than you imagine. It's stranger than you can imagine. By the end, you might not look at a clock the same way again. The malleable nature of time before we can even head toward a black hole. We have to tear down an idea that feels unshakably true in our daily lives. That time is constant. We live by the steady tick-tock of the clock. A second is a second. A minute is a minute. It feels absolute, the same for everyone, everywhere. But one of the biggest shifts in modern physics, thanks to Albert Einstein, was the revelation that this just isn't true. Time isn't a rigid, universal metronome. It's relative. It's flexible, and it's tied to space in a four-dimensional fabric called spacetime. Think of spacetime like a huge, flat, rubber sheet. Now, place a bowling ball in the center. The sheet curves and dips around the ball's mass. This is exactly what massive objects do to they create a curve, a depression, and that curvature is what we feel as gravity. It's not some mysterious force pulling us. It's the actual shape of spacetime, bent by the mass of the Earth, telling us which way to move. But here's where it gets really interesting. It's not just space that gets curved. It's space. This means the flow of time itself is affected by this curvature. The deeper you are inside one of these gravity wells, the slower time flows relative to someone in a weaker gravitational field. This isn't just a theory. It's a physical reality we have to account for every single day. You probably have a device that relies on this principle. Your smartphone. The Global Positioning System, or GPS, is a network of satellites, each carrying an incredibly precise atomic clock. Those satellites are farther from Earth's center of gravity than we are, so they're in a weaker part of Earth's gravity. Because of this, their clocks ticked just a tiny bit faster than ours on the ground. The difference is minuscule, about 38 microseconds a day, but if engineers didn't correct for this gravitational time dilation, the errors would add up fast. GPS navigation would be off by about 10 kilometers every single day and fail within minutes. So, every time you use a map on your phone, you're using a practical application of Einstein's theory, proving that time flows at different rates depending on gravity. The fact that an astronaut on the International Space Station ages just a little slower than their twin on Earth is a verified, measurable fact. So, we've established a fundamental rule of the universe. Gravity warps time. It's a subtle effect here on Earth, but this connection between mass and time is the key to understanding what happens. When we take it to the most extreme place in the cosmos, we've seen what a small dip in spacetime from our planet does. Now, let's see. What happens when we approach an object so massive it doesn't just create a dip in that rubber shit, it punches a hole clean through. The journey to the edge of forever, alright? Let's put ourselves on an interstellar spaceship, heading for a stellar mass black hole, an object with the mass of 10 suns crushed into a sphere just 60 kilometers across. Our mission is to send a robotic probe, Observer 1, as close as we can to the point of no return. The event horizon. We're parked at a safe distance, where the black hole's gravity is just a gentle tug. From here, it looks like a perfect circle of absolute blackness against the stars. And it doesn't suck. That's a huge misconception. From this distance, its gravity is no different than a star of the same mass. If our sun were suddenly replaced with a black hole of the same mass, Earth would just keep orbiting like always, though in the cold and dark. We launch Observer 1. It has a high-precision clock and a camera feeding us a live signal. At first, everything seems normal. The probe's clock ticks in perfect sync with ours. 1 second on the probe is 1 second on the ship. But as Observer 1 gets closer, something strange starts to happen. Its clock begins to tick just a little bit slower than ours. The closer it gets, the more obvious the effect becomes. We're witnessing gravitational time dilation on a massive scale. Think about the movie Interstellar. Remember the water planet, so close to the black hole Gargantua that every hour on the surface was 7 years for the crewmate on the ship above. That wasn't just sea. It was a cinematic depiction of this very real phenomenon. Our probe, is now in a similar situation, and the time difference is getting extreme. As the probe nears the event horizon, things get truly bizarre from our perspective. The light it sends back has to climb out of that incredibly steep gravity well, and it loses energy doing so. This causes something called gravitational redshift. The probe's bright white lights would seem to shift to yellow, then orange, then a deep, dim red. At the same time, the time dilation becomes infinite from our point of view. The probe's clock, as we see it, slows down until it seems to approach a complete stop. Its forward motion also appears to halt. We see the probe getting closer and closer, slower and slower, dimmer and redder, until it looks like it's frozen in place right at the edge of the event horizon. From our vantage point, it would take an infinite amount of our time for the probe to cross that boundary. We will never see it fall in. It just seems plastered onto the event horizon, a frozen ghost that eventually fades to black as its light can no longer reach us. So from our perspective, time for the object falling into a black hole stops. From our point of view, the black hole has effectively hidden the probe's future from us. But, and this is one of the most mind-bending parts, that's only our side of the story. What did Observer 1 experience? To understand that, we have to switch perspectives. The view from the inside. Let's rewind and ride along with Observer 1. From the probe's point of view, its own experience of time is completely normal. Its clock ticks away, 1 second at a time. If an astronaut were inside, their heart would beat normally. Everything would feel ordinary. But for this astronaut, looking back at our ship, the view would be horrifying. Just as we see their time slowing, they would see our time speeding up. As they plunge deeper into the gravity well, they'd see our ship's clock ticking faster and faster. Days, weeks, and years of our time would flash by in seconds of theirs. Looking out at the rest of the universe, they would see stars streaking across the sky, watching the future of the cosmos unfold in the moments it takes them to reach the event horizon. As the probe reaches the event horizon, that fearsome boundary, something remarkable happens from its perspective. Nothing. For a large enough black hole, the event horizon isn't a wall or a fiery gate. It's just an invisible line in space. The probe would sail right across without a jolt or a flash, with no sign that it just passed the point of no return. But the universe has fundamentally changed for it. Once inside, space and time have effectively traded places. For us, outside, we can move freely in 3 spatial dimensions, but are stuck moving forward in time. Inside the black hole, the direction toward the center, what we once knew was forward in space, is now the future. The astronaut can no more stop themselves from moving toward the center than we can stop ourselves from moving into next week. The flow of time is now a physical current, dragging everything inward. All possible futures lead to one place, the center. To escape would mean traveling backward in time, which is just as impossible inside the black hole as it is out here. This is the true, bizarre nature of a black hole. It doesn't swallow time. Its immense gravity warps spacetime so much that time itself becomes a direction, and the future becomes an inescapable location. For smaller stellar mass, black holes, there's another, more gruesome effect. The tidal forces would stretch an object, pulling it apart into a stream of atoms. However, for the supermassive black holes at the centers of galaxies, an astronaut could cross the event horizon completely intact, unaware of their fate until much later. So we have 2 totally different, but equally valid realities. The reality of the outside observer, who sees an object freeze and fade at the edge, and the reality of the infalling object, which experiences time normally and crosses the boundary without an issue. Physics allows both of these to coexist because the event horizon is an ultimate information barrier. Since the infalling observer can never send a signal back out, their contradictory experience can't create a paradox in our universe. The final mystery and conclusion. So where does this journey end? For the astronaut and for our understanding, inside the black hole, all paths lead to the center, to a point called a singularity. And it's here that our story has to become more speculative, because the singularity is where our current understanding of physics completely breaks down. According to Einstein's theory of general relativity, the singularity is a point of infinite density and infinite gravity, where all the black hole's mass is crushed into 0 volume. Spacetime curvature becomes infinite, and our equations just stop working. Time, as we know it, might very well end there. But general relativity isn't the final word. It doesn't include quantum mechanics. To truly understand the singularity, we'd need a theory of quantum gravity, one of the greatest unsolved problems in physics. Some theories guess that the singularity isn't a point, but maybe a wormhole to another universe. Others suggest quantum effects prevent a true singularity, replacing it with something like a Planck star. The truth is, we simply don't know. What happens at the heart of a black hole is a mystery, shielded by the one-way door of the event horizon. So, let's get back to our original question. Do black holes really swallow time? The answer is a beautiful and complex no. They don't consume or destroy time. Instead, they are masters of it. A black hole is a place where gravity is so strong that it bends the fabric of reality, creating a profound split between those who fall in and those who watch from a safe distance. For the outside observer, a black hole is a time thief, seeming to freeze the clock of anything that gets too close, stretching a few moments into an eternity. The object is effectively removed from our view, its future timeline forever inaccessible. For the traveler falling in, the black hole is a time machine to the end of the universe, where their own clock ticks on normally while the history of the cosmos flashes before their eyes. The truth is far stranger than the myth. Black holes aren't cosmic vacuum cleaners. They are the natural, extreme result of gravity's effect on space. They challenge our most basic ideas about time and reality, showing us that time is a local, flexible thing that can be stretched and warped. They are the ultimate cosmic laboratories, pushing the laws of nature to their absolute limits and pointing us toward a deeper understanding of the universe. Time isn't swallowed. It's transformed into something so alien, it defies our everyday experience. The paradox of time at the edge of a black hole is one of the most fascinating ideas in all of science. What do you think about it? Does the idea of two completely valid but contradictory realities existing at once bend your mind as much as it does mine? Let me know your thoughts down in the comments. I read as many as I can, and your questions often spark ideas for future videos. And if you enjoyed this journey into the bizarre physics of space-time, make sure to subscribe and hit the notification bell, so you don't miss our next exploration into cosmic mysteries.